Welcome back for the last two panel discussions in the physics conclave. We're going to have a very fascinating panel discussion on a topic which a lot of students here and also many of the members in the physics community are interested. And that is theoretical high energy physics and gravity. And we have outstanding panel members here who are part of the panel discussion, starting with Professor Sunil Mukhi, Seema Sharma, and Sunil Mukhi, Sudarshan Anant, and Sunita Varadarajan, and Sachin Jain, and Deeptimai, of course. Deeptimai is also part of it. So may I request the panel members to go on the stage, please? So as usual, the instruction goes that during the interaction session, the students will get the higher priority to ask questions, followed by the faculty members. So we strongly encourage all of you to ask as many questions as possible. And we can start, and hopefully Sachin is going to join us very soon.
He's coming to join.
Round of applause. Yeah. Okay, we are on time. We can get started. Yeah, Sunil.
Okay, welcome everyone. So I will speak for 5 minutes, just giving a very broad overview of this subject called theoretical high energy physics and gravity, just mainly for the students. After that, Deeptimai will speak for 3 hours and then we'll go for dinner. Okay, that was a joke. After that, all of them will speak for 5 minutes each. We will try to wrap up our part in 30 minutes so that we give the audience 30 minutes, but you know, it doesn't always work. But I better start in any case. Quantum field theory is the most successful formalism known to accurately describe particles and forces. And it originated in particle physics, but in the spirit that all physics is connected, it has spread far beyond that, and it now influences a wide variety of branches of physics, and I'll try to highlight that point. Then my colleagues will talk about their individual work. So in elementary particle physics, we have one quantum field for each particle. So photon has its field, gluons, leptons, quarks, Higgs, everybody, etc. Everybody has their own field. And then the fields are written together with some interactions, and then we can calculate things, which I'll talk about on the next slide. The remarkable fact is that in condensed matter systems, we want to study the statistical physics behavior of quasi-particles or collective excitations, which have names like vortices, phonons, plasmons, magnons, and so on. And we can assign fields to those also, and we can study analogous quantities mathematically, but which have a completely different meaning in the condensed matter context. So in this way, it's a tool which you can, it's a hammer which you can use to hammer on different subjects. It's also useful in cosmology, where in fact it combines both the quantum and statistical aspects and even classical aspects. And one of the things I just quickly say here is that as far as we expect, the experimentalists haven't been able to tell us the nature of dark matter, what spin the particles have or how they interact, but if they would tell us all that, we would add them to the Lagrangian of our field theory. So in that sense, we believe that even dark matter is not something mysterious from the field theory point of view, just that when we know better what it is, we'll add the corresponding information into the field theory. So that's a broad brush picture that at least 3 big subjects that quantum field theory acts on. To be honest, of course, it is most preeminent still in particle physics, but increasingly has a foothold in these other two subjects. And let's talk about now what we do with it. So what can we do? What can we use QFT for? In principle, we can calculate partition functions, correlation functions, scattering cross-sections, bound states, decay rates, lots of things. But I say in principle because this is true only if the QFT in question can be accurately solved, and this happens usually only if it is weakly coupled. So if the system is strongly coupled, then it's very difficult to actually solve it, even if we know or believe we know what the theory is. Now, for specific models, one is the standard model of particle physics you heard about this morning. One is, for example, models like superfluidity or superconductivity. And one class is the lambda CDM models of cosmology. It gives quite clear predictions in many situations, which can be and have been compared to experiment. Apart from giving precise answers, it also illuminates the underlying physics. For example, renormalization group flow is an absolutely mind-blowing sort of reinterpretation of how field theory works, where it's different at different energy scales. And we learn a lot from that. That brings us to conformal fixed or invariant fixed points. There are effective interactions which field theory gives us. There are symmetries. There's breaking of symmetries. Nowadays, there are non-invertible symmetries. We can understand phase diagrams. So these can also be qualitative or partly quantitative or algebraic, not necessarily numerical results. Now, what do QFT researchers do, the people here in particular? They study fields and their interactions not necessarily with any experimental application in mind, but to understand and classify the structures, to discover the possible mechanisms, effects, and phenomena. And there are famous examples of these effects and phenomena which cut across fields, and I'll come to those. Well, I'll come to it right away. The Kibble-Zurek mechanism, I was quite excited to hear about it in the last talk on active matter and on soft matter and active matter, where Vijay Chikkadi mentioned it. In his context, I assume it is some formation of, so originally it was a study in QFT, so Kibble is a field theory person with interest in cosmology, and he wanted to study the formation of topological defects in the early universe during structure formation. So he provided some general theory of this mechanism of formation of defects. Interestingly, his defects have never actually been seen, as I understand. So the early universe physics does not show us domain walls, and in fact, inflation, I think, is partly a way to go get out of this problem. However, the same domain walls show up in other systems, and just to give you an idea, here is the title of Kibble's paper, Topology of Cosmic Domains and Strings. It's from a high-energy lab. Look at the second paper, Zurek. Cosmological experiments in superfluid helium, ? And he is in an astrophysics lab in Los Alamos. So I hope from this you can see the kind of broad sweep of the subject. Now to wind up, I'll just say a few words about gravity. Gravity is general relativity is, of course, the most successful formalism to study the gravitational field and its coupling to matter. It was invented by Einstein to do this. Its basic object is the metric function of space-time, g mu nu of x, and that's a field. It's like the fields that I mentioned before, like photon, gluon, etc., but it's also very different. And maybe later in this discussion, I might mention again why it's different. Now, allowed spacetimes must solve the famous Einstein equation. This is the Einstein equation. I'm sorry about that half. It's some bug in Keynote. And this number, lambda, in the equation is the cosmological constant, and this is what is referred to commonly as dark energy. So to answer also Shauvik's question of yesterday, this is a different kind of energy. It is not convertible to matter because it's a vacuum energy density. And it is a very special feature of general relativity. You may know that Einstein thought this was a mistake. Turns out experimentally it's probably true. In gravity, in general relativity, gravity acts not as a conventional force, but by distorting the structure of space-time. Some examples of such distortions are black holes, gravity waves, cosmologies, or even the Earth's field that we are all living in are all distortions of space-time. And here's the first ever picture of a black hole. They're very ubiquitous in the universe. In fact, they distort the causal structure of space-time so much that both ingoing and outgoing directions from the black hole are ingoing. If this sounds like a paradox, well, it's my summary of Penrose's Nobel Prize-winning 3-page paper. And you can read about it. Now, we would like to quantize this theory so that it can be part of quantum field theory. We may not need a separate topic called gravity if it becomes incorporated in quantum field theory, but this hasn't gone perfectly well. And fortunately, there's plenty to understand at the classical and semi-classical level, and we'll hear about that also. So with that, I request Sudarshan to please come and talk about his work.
Okay, so good evening. Let me start with, I don't know why I've written this. The first line refers to Einstein's field equation that Sunil just showed you. So there are huge number of reasons why we want a quantum theory of the gravitational force. One is it will complete our understanding of the four forces of nature. But there are various other reasons, including, for example, being able to simply explain why things fall down, right? So, the reason I've said unhappy equation is because at a very, very loosely speaking, Einstein's field equation, famous equation, relates curvature of space-time on one side to mass that curves it on the other side. And the mass is quantum mechanical, right? Matter is quantum mechanical, space-time is classical, so the equation makes us a little unhappy. The equation itself is unhappy, is the claim. The minute you start trying to quantize gravity, if you have learned, for example, path integral quantization, you can see that dimensional analysis will tell you that divergences are going to be a problem in quantizing gravity. And we are struggling with the complete lack of experimental input in this field, okay? And this you can look up on the internet, why experimental inputs are somewhat limited for the gravitational force. You'll hear more about this from other sources, but traditional experiments don't work because gravity is so weak. So we turn then to symmetries, because for non-gravitational forces, it turns out that symmetries are what help. And how do they help? Very naively speaking, let me just say this, that if a process is never observed in nature, it's because it violates some symmetry principle. And this can go into a whole philosophical discussion about what Wigner called the unreasonable effectiveness of mathematics, which is why does nature care about math? Okay, I don't know, and we'll leave that for a separate discussion. But it is therefore very tempting, and if you look at the last 5-6 decades of progress in physics, the orange line has been very effective, which is you look for these divergences or infinities, you find ways to fix them, and that takes you forward. So this is a bottom-up kind of working approach to how you can fix these divergences. So broadly speaking, one-line summary of what I've said so far: symmetries have to rescue us when dealing with the infinities of gravity. So I thought I would highlight briefly 3 themes of interest as far as symmetries are concerned. So the first is space-time symmetries themselves. The slide contents are a little technical. Let me just make the broad point. If you look at there is a calculation you do with quantum chromodynamics called the beta function of QCD. And if you look at this result for the beta function of QCD, it was pointed out that these numbers in black, these factors in black, they come from what is called an internal symmetry group, SU3. The numbers in blue, however, are not merely numbers. It was pointed out by Hughes that they could be understood in terms of space-time spin. So in fact, you can link them to space-time symmetry. Now, this is not so shocking because the 2 ingredients in any quantum field theory are the fields, particles, their interactions, and the stage on which you are looking at these particles and their interactions. And that stage is space-time. So it's not very surprising that the 2 groups are the internal symmetry group and the space-time group. Now, Cartwright extended this result to, the result has now been extended to 2 loops in QCD. But let me talk about supersymmetric field theories. These are quantum field theories with supersymmetry in 4 dimensions. Cartwright extended this Hughes observation to in the n equals 4 super Yang-Mills theory. Now, if you've not heard about it, let me simply say it's the harmonic oscillator of high energy physics today. People love this theory because it's ultraviolet finite. In fact, it's better, it's conformally invariant. And so it's used as a toy model for almost everything, from ordering coffee to calculations. And what Cartwright showed was that if you could think of this theory as having a 10-dimensional origin because the fields combine nicely in 10 dimensions. And the group theory of 10 dimensions is governed by a group called SO8, special orthogonal 8. And that has this beautiful Mercedes symbol as its Dinkin diagram and a property associated with it called triality. So what Cartwright showed was that every cancellation in the n equals 4 Yang-Mills theory, all the infinities that cancel out are exactly because of this triality property of SO8. Two-loop result. Now, if you carry this over to n equals 8 supergravity, let me explain what this is. This is Einstein gravity with a lot of stuff tagged on so that there is supersymmetry. It's maximally supersymmetric gravity in 4 dimensions. Then it turns out the parallel analysis says you have to look at a group called SO9. And there you see a mismatch in Dinkin indices telling you that there should be an infinity at either 4 loops or somewhere thereabouts. So this brings us then to the question of how, what kinds of symmetries these theories have and how one hopes to tame them. And those are called exceptional symmetries. So the supergravity theories, one hope for them being finite is these exceptional symmetries called E6, E7, E8, which accompany supergravity theories in dimensions 3, 4, and 5. And why this is interesting is 2 reasons. One is the exceptional symmetries may be, for example, the 4-dimensional supergravity theory has an E7 exceptional symmetry. It may be a large enough, powerful enough symmetry to make the theory more finite than people believe. And remember, we are rather desperate at this point to see if any quantum field theory of gravity can be rendered finite by any means. So connecting to the real world is a little low on the priority list at this point. What is interesting about exceptional groups, let me highlight for today, is that when you go down to 2 dimensions and then 1 dimension, it looks like, following this chain of logic, the symmetries involved are what are called infinite dimensional Kac-Moody algebras, E9 and E10. Particularly E10 is interesting because then you're in 1-dimensional space-time, which is time. And so there's this idea that if you understand this well, then you'll understand how space emerges, because you've started with time and how do you get space. I don't know more about this at this stage, so nothing I say will make sense, so I'll stop there. The other symmetry I want to highlight is higher spin symmetries. There is this model by Vasiliev where he claims that an infinite dimensional higher spin symmetry renders gravity in 4 dimensions finite. So that's interesting. I'm interested in looking at that. It mostly formulation in de Sitter background. So for students in the audience, which is the majority, the 2 things, I think Sunil highlighted the importance of quantum field theory. I would also highlight the importance of learning de Sitter physics well, given its relevance to our universe. Okay, last slide. I'll wrap up in a minute. In 2044, if there is a giant bonfire and everybody burns all papers written with supersymmetry in them, I need a backup plan. So this is my backup plan. So I'm also interested in this. This is non-supersymmetry, non-higher dimensional stuff. Sunil already told you that scattering amplitudes represent the physics in a quantum field theory. I'll tell you the following interesting observation from now 2 decades ago, that when you calculate scattering amplitudes, let's say you want to study QCD 4 gluon scattering. So 4 gluons means you have to calculate 4 Feynman diagrams. Feynman diagrams are these funny squiggly things here. 5 gluon scattering, 25 diagrams, and you can see this gets out of hand quickly. 8 gluon scattering involves 35,000 diagrams. So you give your PhD student this, the student is very unhappy, very tired, comes back after a year and says, okay, now I'm irritated because the results are like this. Either a large class of amplitudes are 0, or they all have this nice structure. So a large number of these diagrams mysteriously gave simple expressions. Why did you waste my time? So then you just make an excuse and run away. But the point I want to highlight is that it looks to me a little bit like this search for beauty in the last century may not be the way to go in the future. So I've struck out the word beauty here. By beauty, what physicists mean, let me explain. This is beautiful for you so that you have a dictionary for the rest of the discussion. This is beautiful, this is ugly. Okay? That's the... sorry, I didn't realize that. The equation on the left-hand side, F mu nu is considered beautiful. The equation on the right-hand side is considered ugly. This is convention, so please don't question it. One of the key points I'll end with this is that manifest Lorentz invariance and manifest locality, while good, may have been obscuring some of the physics we are after. So perhaps we should, in some of these theories, one of the guiding principles is look for the physics and don't worry about the simplicity of the theory. I'll stop with that. Thanks.
Okay. Relax. We have 3 hours. So, So, okay, I won't take more than 10 minutes because they have also taken 10.5 minutes each. You see, 21 minutes for 2 speakers. Okay, so, I'll start talk. Okay, so one of the things I'm interested in is to understand quantum field theories, or in particular effective field theories, or rather understand effective field theories which are, or recognizing effective field theories which are quite deceptive. As you might know that recognizing deceptive personalities can be quite challenging. So in this case also recognizing deceptive QFTs can be quite challenging. Now, why effective field theories? Because effective field theories, as Sunil also pointed out, they find applications in pretty much all areas of physics. Particle physics, cosmology, and also in condensed matter physics. In particle physics, we have all learned about Fermi theory, chiral perturbation theory, and in condensed matter physics, we have learned about Landau-Ginzburg's theory of superfluidity, and so on. So they are pretty universal, and so it makes sense to try to constrain the space of these theories and understand which ones are consistent and which ones are not consistent. But for that, I have to tell you what I mean by consistent. What I mean by consistent is the following. So consistent either with a consistent theory of quantum gravity, which in general is a pretty hard question, and I don't work on that, mostly because of my incompetence. So I'll ask a simpler question, that whether it can be consistent within a Lorentz invariant field theory alone. So I have a theory at low energies, and I'll ask whether this is consistent, assuming that the microscopic theory where it's coming from is actually Lorentz invariant. And as you all know, that Lorentz invariance had been proved to death, and so it's very mild assumption on what we want to do. Now it turns out that it is possible. In fact, theories which I have in these slides, this Lagrangian, the first term is Maxwell's Lagrangian, and then there are 2 terms which the form of these terms were written down by Euler and Heisenberg in order to explain photon-photon going to photon-photon scattering. Because as you know that Maxwell's theory is free and photons don't scatter of each other. So Euler and Heisenberg wanted to scatter photon and photon and see what Lagrangian he can write down to explain photon-photon scattering. Now, this theory which I have written down, you see, naively looks perfectly consistent. This is Lorentz invariant, gauge invariant, and so on. But it turns out that this theory is inconsistent with very basic principles of quantum mechanics and special relativity, namely unitarity and relativistic causality inbuilt in at least in classical relativity, and microcausality if you include quantum mechanics there. So while quantum mechanics and relativity have given us very powerful tools to constrain these effective theories at low energies, it's not clear whether we have exhausted the full power of quantum mechanics and relativity in constraining the space of EFTs. The cartoon, you can see this green region or this whole space as the space of very healthy looking effective field theories. The green region would be inconsistent if we do such an analysis. In the context of quantum gravity, this is often called swampland, but since I'm not interested in quantum gravity, I'll call it wetland. And the hope is to constrain and get the consistent theories in this circular region, which they call landscape, but I have called here countryside, because that's what the synonym which Google suggests. And the final hope is to constrain it so much that we get finally one or two theories. One of them will be the standard model of particle physics, and then our experimental friends Saurav and Sima would be completely irrelevant. So we'll just, by theoretical consistency, we'll constrain the space of theories so much that we know what the unique theory of nature is, and we don't have to do experiments to figure out what the correct theory is. So that will practically never happen. So they will always be relevant. And if you want to see more about it, you can see the poster by J. Desai. Okay. The other topic I have been interested in the last few years, mostly with my student Farman and Suprita, is to try to understand quantum field theory in de Sitter space. As Sudarshan told you to learn about de Sitter space, I'll tell you more reasons to learn about de Sitter space, because at least my motivation to learn about de Sitter space is that it's relevant for real world, is relevant for inflationary cosmology, and is actually also relevant for the universe today, because of the accelerated expansion of the universe. You might know that we are entering into a de Sitter phase. So is both relevant for very early stages of the universe and also for relevant today. So it makes sense to try to understand de Sitter space and how quantum field theory works in de Sitter space. Now these are some important non-trivial aspects of de Sitter space. I'll just run you through them and stop. Now in de Sitter space, due to the dynamical nature of the de Sitter space, it turns out that the vacuum is not unique. This is very similar to a harmonic oscillator where the Hamiltonian is time dependent. If you have solved this problem, you would actually know very many non-trivial features of QFT in de Sitter space. Because you have a time dependent Hamiltonian, the vacuum is not unique, and if the vacuum is not unique, you are confused about what to call particles, how to define particles. So that's why the very definition of particle is very confusing in de Sitter space, and hence there is no natural choice of the S matrix. It has been tried a lot in recent years also to try to understand and define S matrix for de Sitter space. More technically, in de Sitter space, if you try to compute, let's say, 2-point correlation functions or n-point correlation functions, you see a lot of infrared divergences, in particular at distances which are at large distances. This makes life complicated, and this also needs to be understood. Also, since in de Sitter space the space is expanding, if you take any wavelength, now this wavelength in the past will be blue shifted, and in the future will be red shifted. So a wavelength, if you a particular scale of the wavelength, if you take that was very small in the past and that will be very large in the future. So the very idea of scale separation, which is at the which is a central point in physics at least in flat space, and the central point of effective field theories is very non-trivial in this case. So that poses one more difficulty in trying to understand effective field theories in de Sitter space. And finally, due to the existence of horizon in de Sitter space, a lot of quantum correlators which you calculate in de Sitter space, they exhibit behavior akin to a thermal state. Now, this is interesting, and this can have implications for studies of quantum information, holography, and also thermodynamics and de Sitter space. This is also one thing I keep worrying about once in a while. I'll stop here.
So I was a bit embarrassed because people clapped when I came in. Because I was late again. It was not my fault, and this is the kind of first time I'm seeing a conference where I hear about dark matter conductivity. There is a comma in between though. So
both are two different topics. It's very rare that you learn about dark matter as well as conductivity in a material. So those were very exciting. And also I'm a bit embarrassed that my talk will be a little informal as compared to, but good thing is that it will be connecting also quantum field theory to the gravity also, which will be discussed a little later. Before I go on, Sakil, my student, he was complaining that there is no session for quantum open system. So it's just advertisement for him that he works on quantum open system. If you want to know more about it, you should go to his talk, but to his poster. But I'll summarize. It's like Navier-Stokes equation for quantum mechanics, okay? Which is applicable. People apply to single particle quantum mechanics, multi-particle, as well as recently Sakil is also thinking about cosmology, where he's trying to apply this. Okay. So as you can see with the poster, star of the show is conformal field theory. CFT is a star. And its application, quantum field theory was discussed. Sunil emphasized the importance of quantum field theory. But quantum field theories are defined through CFT. Fundamental objects are conformal field theory. Quantum field theories are like the deformation from the CFT. Via ADS CFT duality and other duality, conformal field theory plays an important role in defining what is quantum theory of gravity. That's also another very important aspect. Cosmology and early universe that Titimay was also talking about. Yesterday I was also talking about using conformal field theory technique, you can understand CMB correlations. String worldsheet is described in terms of conformal field theory. So again, you see a beautiful connection over there. Phase transition, condensed matter. Actually, this can become n point function over here, but I'll just stop here. One most precise result in 3D Ising model, critical exponent, actually came from CFT bootstrap, which has surpassed Monte Carlo simulation. Nothing to boast or nothing, it's just a fact, okay? There is nothing, both are equally important thing, Monte Carlo as well as CFT bootstrap. But here I just wanted to highlight that, these techniques are also useful in various important other things. Before showing my most informal slide, I would like to say one contrasting point of view than what Sunil pointed out, that quantum field theory is about fields. But when you have very strong coupling where the perturbation physics, which we learn in the class, does not hold, also the field picture is not very, very useful. There you have to develop something else. Conformal field theories are the subjects which are mostly strongly coupled, okay? And there the usual field theory techniques are not going to work. Those are only the non-perturbative techniques where symmetry, causality, positivity, those kind of unitarity, those are the kind of techniques which play the most important role. Okay, I'll go to my most informal. Only these two pictures are from ChatGPT, okay? Others are my original. My originality here to ask the ChatGPT the question. So I study conformal field theory. One of the topics I study is conformal field theory. And conformal field theory is traditionally studied in the position space. As I see, it's very crowded and a lot of people, I also have worked, a lot of people are working and still working. It's profound and it has led to very interesting discoveries. But however, often in research, we are forced to take different routes which are not very well lit, okay? And this is the route I'm talking about. It's the study of conformal field theory in a little different variables, which started from momentum space, Fourier space, went into Spinor-Helicity variable. Then now we are in the twistor space, as I am going to go about why they are important. So right now, so my path right now is the curiosity path, which is we are trying to make the path little brighter and collect as many jewels in the path which are there. Collect as many jewels as possible while going through without having a bigger, like we have lots of wishes which we want to solve, and there are a lot of excitements ahead, but I don't really know what is the, what would be, there are fundamental questions that I would like to address, but I don't know whether, how will I be able to solve them. But right now, our aim is to just collect all the jewels, okay? So, here are, I'll discuss, here are some of the jewels that I feel we have collected. In the left, what you see is a circle where one node is free harmonic theory, another node is free bosonic theory. There was it's a remarkable duality, exact duality which does not require supersymmetry on anything, which connects free harmonic theory to free bosonic theory using something called Chern-Simons, which is a little more complicated gauge field theory. What we were able to do, so it's a theory, Chern-Simons theory, which actually, if you just calculate, you will be able to show that it takes you from boson to fermion. So what we are able to show that even though this is very, very complicated theory, very, very complicated interacting theory, we are able to map this complicated interacting theory correlation functions, which are the most important topic here, to the free theory. And this question was actually very, very interesting and is also interesting today. I have been very closely involved in the development of this, and 5 years ago, these were the most fundamental questions that people would be asking very often. But as the nature of our field, people forget about those questions, most complicated questions. Even though I did not try to solve this problem directly but as I said, we are trying to clarify some things in a different way in conformal field theory, and this is the jewel that we pick up, that we are just able to solve this problem using the formalism that we developed, okay? That's one of the jewels that I'll say. The second jewel I'll talk about, that these same theories are also dual to gravitational theory, which Sudarshan was talking about, Vasilyev theories, okay? These are higher spin theories. It turns out very recently there has been discussion about whether the Vasilyev theory by itself is actually a consistent theory or not. Vasilyev theory is defined de Sitter space as well as anti-de Sitter space. In the context of anti-de Sitter space, at least it was found that it may not be local, which was one of the fundamental assumptions in writing, or fundamental assumption in writing Vasilyev. Vasilyev was, people were really, people thought that that is one of the theories which is contains all possible higher spin theory, but also local at the same time. Somehow that people don't believe anymore. So what 5 or 6 years ago, people found out a subsector of the Vasilyev theory, which they called chiral higher spin theory, which is same as what Pavan was showing, something rotating one direction, other thing was rotating other direction, this chiral versus anti-chiral. People found out the chiral subsector, which is neither unitary, it was not a unitary theory, which they thought it was local. Also, they thought, they said that it's a very nice and interesting example of a higher spin theory. The question was open that what would be a CFT which actually is dual to that. And this is what, with a paper with Dhruva and other people, we actually gave a nice prescription how to identify that CFT. If you want to learn more about it, Dhruva has a nice poster about it. All this led to, so these are the jewels that I have collected, but we have collected. All this has led to some interesting questions that we are trying to understand. So first question is, since there is a theory which now connects from free boson to free fermion, can I write down a free theory of anyons where I'll just define a field which will behave like anyons, and their free theory correlation function without interaction will give rise to all the complicated correlation function. This is one of the questions that we are thinking and not thinking. The other question that we are now very excited about, and you will see more, you have already seen more about it in two of the posters, Deep and Ashwini. Here is to understand what would be a geometrical picture for a conformal field theory. Okay? So by that, what I mean is the following. Nima Arkani Ahmed, 10 years ago, wrote a remarkable paper, n is equal to 4 super-Yang theory, where his focus was on n is equal to 4 super-Yang theory. He showed the following, that in quantum field theory, or space and time are fundamental thing. That's how we do quantum field theory. And locality is of the most important thing, that the two interactions happen at a local point. Okay, that is the one of the most important thing. But as Sudarshan pointed out, that leads to a lot of trouble in calculating scattering amplitude. Even if you want to calculate 5-point function whose answer may be very simple, you have to calculate 5,000 diagrams, or many more, 35,000 or something, some number of diagram, So what Nima et al. Proposed that this locality idea, suppose I get rid of, he proposed that this scattering amplitude can be actually described in terms of some geometrical object. They call it amplitude hadron. And the volume of this geometrical object will be given by the scattering amplitude. Okay? Now, very recent, like this week, we have just written a paper on understanding conformal field theory in twistor space. Twistor space is just mapping lines into a point. And this is the first step towards actually understanding this geometrical picture. Okay, I'll finish it here.
Okay, so I work on black holes. So let me just start by saying something which everybody knows, that there is now strong observational evidence for black holes. Okay, so this is, in my view, this evidence is incontrovertible, but there are, of course, people still working on whether there are some things called black hole mimickers, but there's very strong observational evidence for black holes. Now, black holes are very strange objects. Okay, so you might have known that nothing ever comes out of a black hole, but that's not the only strange thing about it. In a sense, a black hole is a thermodynamic object. So it obeys laws which are similar to the laws of thermodynamics. And this is not just analogy, it goes much deeper. So for example, if you take a space-time in which there is a black hole, you have a cup of tea and you're standing outside the black hole, you throw the cup of tea inside, then the thermodynamic entropy of the outside has decreased. Okay? So there is a violation of the laws of thermodynamics unless you say that a black hole also has some entropy. Okay? So Bekenstein was the first person who proposed this, and he had a lot of reasons to speculate that the entropy of a black hole was proportional to a geometric quantity associated to the black hole called the black hole horizon area. Okay? So if you have a black hole region in space-time, then you look at the boundary of that black hole region at an instant of time, then the area of that boundary is called the black hole horizon area. And Hawking proved many years ago that in any classical process, the black hole area can only increase. So for example, if you have two black holes merging to form one, then the combined areas of the two black holes will be less than that of the final black hole that is produced. Okay? So in all classical black holes, in all classical processes, this black hole area seems to increase. So Bekenstein proposed that the entropy of a black hole should be proportional to its area. Okay? The proportionality constant was fixed much later, but basically the black hole is like a thermodynamic object. So you might ask that in thermodynamics we have systems which have some thermodynamic entropy, which you can explain through some statistical physics. You can think of some microstates which correspond to this system macrostate, and you can think of the entropy as the log of the number of microstates. So can you do that for a black hole? And that lots of people have worked on. People have tried to reproduce the entropy of a black hole in a microscopic quantum theory of gravity. So that's one interesting aspect of a black hole. And then what Bekenstein proposed was that, for example, in Einstein gravity, you consider the sum total of the entropy of a black hole and the thermodynamic entropy of the outside. Okay? And he proposed that in any physical process, the sum of these things is not decreasing. Okay? So this combination is called the generalized entropy. Now, of course, you can also consider something more general. Instead of having classical matter outside a black hole, you could have quantum fields outside a black hole. Then there's a very specific formula for this entropy of the outside. And then the conjecture that Bekenstein made was that in any process, both involving classical matter and quantum fields outside a black hole, this quantity never decreases. Okay? So this is called the generalized second law. What I have done with my student Mohammad Ali recently is that we have worked on various proofs of the generalized second law. Okay? So there are various proofs because you could not be strictly in Einstein gravity. There are many theories like string theory, for example, which propose that there are corrections to Einstein gravity. And in all such theories, you could define a generalized entropy. Okay? So what we did recently was we used techniques from von Neumann algebras to prove the generalized second law for not just Einstein gravity, but for all these general classes of gravity theories which have a symmetry which we believe gravity theories should have, which is diffeomorphism invariance. Okay? And the techniques that we used are quite new. They are to do with a structure called a von Neumann algebra, which describes everything from qubit systems to quantum field theory. And so using those techniques, we were able to prove the generalized second law in various situations. Now there is actually, so first, one more interesting question which we are working on now is there a quantity which increases in this system which goes beyond the approximation of semi-classical gravity? So all the proofs of the generalized second law have been in the approximation of semi-classical gravity, which means that gravity is treated classical and matter could be quantum. Okay? But that's an approximation. We know that actually gravity is also quantum. So is there some quantity which is non-decreasing, even going beyond the semi-classical approximation? Okay. Now let me just go a little bit deeper into let me go a little bit deeper into the connections between black holes and thermodynamics. Now Hawking showed that a black hole radiates like a black body at a certain temperature. Okay? And the temperature you see I've written here, it is 1 divided by the mass of the black hole modulo some constants. So this is not the physical temperature of the black hole. The black hole is actually a very cold object. But what he showed was that if you have quantum fields outside a black hole, then a black hole radiates. Okay? And it radiates, its radiation is approximately the black body radiation, which only depends on the temperature. Now if you see the temperature, you see that the mass comes in the denominator. So if I have a black hole radiating away, then its mass gets smaller and smaller. The temperature gets hotter and hotter, so finally it's going to completely evaporate away. Okay? But the black hole could have been formed from some quantum matter, okay, in a particular quantum state. But now if it's going to evaporate away and emit only thermal radiation, there is a loss of information about the initial state that was used to create the black hole. Okay? So this leads to something called the information loss paradox. So does the black hole, lose information, okay, when it Hawking radiates away? Now there's a lot of work which people are doing now, which is to ask, is there truly a loss of information in this process? Okay? Or does the information come out subtly in the radiation? So for example, it's not perfect thermal black body radiation. Does it come out subtly in the radiation, and can it be recovered from the radiation? Okay. So I mention this because recently there has been a lot of progress in answering these questions. And in fact, a lot of progress, but that answer is for black holes in space-times with a negative cosmological constant. Okay. So the challenge for us is to understand this better for the black holes that we actually see in our universe. Okay. And one of the things that I'm working on with my student is to understand this entire evaporation and information recovery process in the language of this von Neumann algebras. So I'll stop here.
Okay, so obviously we didn't do very well with time, but so in the interest of time, I'm going to only talk about one of my 2 slides. And the idea is that if a question comes up which will prompt me to show the second slide, only then I'll show it, but I won't tell you what it's about. It's on a different subject. Okay. So so this has come up, conformal field theory has been mentioned by many people already. So the key idea is that at low energies, all quantum field theories flow effectively to a fixed point, and they acquire a new enhanced symmetry called conformal invariance. And for essentially this discovery, Ken Wilson got a Nobel Prize in 1982, one of the few single-person physics Nobel Prizes ever, at least in more recent times. Now, conformal invariance is illustrated by this picture. You can distort a picture or a grid, as long as you preserve all the 90-degree angles in it. That is the symmetry called conformal invariance. And it includes scale invariance, changing scales. So at a fixed point, theories become scale invariant. Such theories are called CFTs, or conformal field theories. And they're especially interesting in 2 dimensions, which is what I've worked on. But let me just tell you some applications: critical behavior for statistical systems, anyons and topological quantum computing, which were mentioned yesterday, string worldsheet theory, Sachin mentioned it, the theory of random surfaces, and also the mathematical theory of modular forms. Now, classifying all quantum field theories is almost impossible, but 2-dimensional CFTs have more symmetry, and there is a chance to classify them at least partially. And if we could do that, we would know about all possible critical phenomena, which is quite an amazing achievement if it happens. And we would also know something about possible non-abelian anyons. Now, during 1988 to 1990, I know where most of you were at that time, nowhere. I started to work on this problem, and then after I came to IISER about 11 years ago, I restarted to work on it with many IISER students, one by one, and we invented new methods in the theory of modular forms to study this classification problem. And 3 years ago, with a collaborator in the US, we achieved a complete classification of all conformal field theories in 2D of single non-abelian anyon type. That means they have one non-abelian anyon. So in a way, they are the simplest anyon theories. There are 123 of them. They fall into 2 categories called semyon and Fibonacci. These words are known to the quantum information people, and I can talk more about that in private with people. So in a certain range of this parameter, the central charge, less than 25, we classified all of them. And I'm very proud of this work because I believe it was the first classification result of a theory, conformal field theories having anyon type excitations, non-zero number of those, since 1984 or 85. Of course, it's a small thing still because it remains a very formal result based on group theory, but it could have an application to topological quantum computing where they exactly want to know the behavior of theories with few non-abelian anyons. That field is still nascent, so we'll see if anything comes of it. So I'll stop here right away, and let's immediately start with the audience questions.
Yeah, the session is now open for questions. Yeah, we'll go with the students.
It may be a naive question, but just for my understanding, that when you start with a particular initial state in the black hole and you end up with a thermal radiation, how does that different from if I start with a particular micro state in a microcanonical ensemble closed system and end up in a very mixed kind of state?
No, so actually this is a quantum state. Okay, you're starting with a pure state. You're ending up with a mixed state. That's the problem.
And this process is purely...
it's not unitary evolution, right?
Yeah.
That's the problem.
So if it is an open system, then that happens in other systems as well.
We are considering the full system of the black hole and the outside. Okay, so you had a black hole forming from a pure state and then ending up evaporating away completely, and you end up with thermal radiation, which is in a mixed state. So that's the paradox.
I had a question. We know that if we give some small but a non-zero mass to gravitons, then they solve some of the cosmological puzzles. But the problem with massive gravity is again about strong coupling. It struggles with strong coupling. So my question is, has there been any recent advancements in biometric gravity or massive gravity that has been able to prove as a viable alternative to lambda CDM, or is it still problematic? Yeah, if we give a small mass to it. Then it solves some of the cosmological puzzles maybe, but it struggles with strong coupling, right?
This statement I'm not completely sure of, because you can have a theory of massive gravity, and then I don't know where the strong coupling is coming from the mass of gravity. So this connection is not very clear to me. And also, I don't think. Now, which problem you said it solves if you give mass to graviton?
Well, I haven't exactly studied about it in detail, but I read a paper about it, so it was there in the conclusion.
No, I think you should probably go back and check what that paper claimed. But I don't think giving mass to graviton will solve a lot of problems in cosmology and so on. In fact, yeah, it will. In fact, there is a strong limit on the mass of graviton because we have seen gravity waves and light coming both. And we know the time of the gravity wave reaching us and also light reaching us. So the difference between the gravity wave speed and light speed, there's a strong bound on it, and that gives a very strong mass on the gravitation mass anyways.
The next question.
Okay, so I saw two slides actually. One was about dimensional analysis, and second one was about black hole thermodynamics, and there was a mention of Bekenstein as well, if I believe. So my question is, if we consider the work of Bekenstein and Hawking, so basically black hole temperature of a black hole, we get m in like mass inverse, like 1/m. So if we consider Bekenstein did a dimensional analysis, he put entropy is proportional to area because entropy and area both increase. And I have been told the dimensional analysis should be voided in theoretical work. So just out of curiosity, I have a question. So what exactly made this entire work to be accepted if we hear the dimension?
No, actually the area by 4G, the 1/4G, that comes from Hawking's work.
Yeah.
Okay. So you have a law of black hole mechanics which looks exactly like the law of thermodynamics, the first law of thermodynamics, if you assume that some quantity is like the temperature. Okay? So that was the stage at which Bekenstein's proposal was. You had the law of black hole mechanics, and you had something which was analogous to temperature. It was just an analogy. Then when Hawking actually went and found out that the black hole radiates like a black body at that temperature, he was able to fix the proportionality constant.
Okay.
So it was only fixed after his work.
Okay. Thank you.
So just to add, dimensional analysis is not forbidden. So
No, not just not forbidden. It's not
Lot.
just not forbidden. It is never fails. I don't know. You said somebody has told you that dimensional analysis is voided in something. No. That's completely wrong. Dimensional analysis is always true. And look, if dimensional analysis was wrong in one formula, it would be wrong in all formulas because you could take those objects to that formula, transform them into some other dimensions, and then we would be having dinner after 15 grams instead of 15 minutes. It doesn't make any sense, right?
So whoever told you to avoid dimensional analysis, maybe avoid them.
Yeah, exactly. Very good. Okay, next question. We still have 5 minutes.
I have not read much about this, but recently there has been some studies regarding applying generalized global symmetry constraints to quantum gravity. So there is some I think there is some rule that you cannot have a global symmetry in theories of quantum gravity, but things like non-invertible symmetries, etc. They have tried applying them to constraint theories of quantum gravity. So I wanted to ask the experts, what do you think of this endeavor and if it can go anywhere? And if it has shown any real promise, because, yeah.
It's a different, generalized symmetries or non-invertible symmetry is a very recent thing, and people have used it to actually describe a lot of already some known things as well as some things which were there. It gives an interesting explanation to various things. For example, even the photon not having mass, there was an explanation using that. So I feel it's a very exciting thing, and people are still exploring. For example, people have used it in a recent work in conformal field theory to explain something which you call as a crossing symmetry. It's not a violation of a crossing symmetry, but it's a new crossing symmetry that emerges, and using that principle only they were able to explain. So I think it's a very useful, and it just people are also exploring right now.
I'll just comment that Fibonacci anyons is the first place that generalized global symmetries were actually discovered, because that anyon, when you fuse it, if you call the anyon as phi, when you fuse it with itself, phi times phi, you get 1 plus phi. 1 is the empty thing, but that can't be inverted back. You can't invert a system like that. Means phi itself doesn't have an inverse. There's no inverse which will annihilate the original anyon. But your question was about applying these ideas in gravity. So yeah, you said correctly that gravity doesn't have ordinary global symmetries. At least that is believed, and there are powerful arguments. Maybe these new type of symmetries, they're not, well, they are generalized symmetries. Maybe they do apply in gravity. It's a very interesting question, I would say.
Just to add what Sunil you said, the anyons are also precisely the place where you start getting this crossing symmetry to be modified. So these are connected.
Same thing, yeah.
Yeah, so Diptima mentioned that, a bit jokingly, that you're going to restrict these theories and come up with one so that a lot of your experimental colleagues are probably irrelevant. So my point is that what is this theory which sort of doesn't have a falsifiability as a criteria? We all think that the scientific theories have a falsifiability as a criterion. Experiments provide such a falsifiability test most often.
Okay, so that was a joke anyway. So once you have a theory, you can test and falsify it. I think there's no question about it. Yeah. So the statement I was making, that in general you have many possibilities of quantum field theories, and then by theoretical consistencies, usually at most you can say that some of them are ruled out, and the rest are all allowed mathematically, and then experimentalists have to see which one is realized in nature. Now, I was just, so now there's a hope that you can make a lot of progress from theory size to constrain these theories so much that finally, okay, practically we will not have one possibility, but at least a bunch, and then experiments have to decide which one is correct. So
yeah.
Just one quick comment. People keep bringing up falsifiability as a criterion. This is because Karl Popper proposed it, and it sounds cute. But I have a question for all these people. Yesterday or today, maybe, Ramki said that Fermi liquid theory applies to a lot of systems, but then there are others now we know which are not Fermi liquids. So Fermi liquid theory is wrong. Is it falsified? No, I'm asking you whether, I'm giving you a theory and asking whether it has been falsified.
This is not a question about theories right or wrong.
It doesn't
It's a question about theories scientific or not.
No, I know, but is Fermi liquid theory scientific considering it works?
If it has a falsifiability criterion, you see, it is a scientific
But
theory.
if it has falsifiability and if it doesn't work for certain materials, then will we say it's false?
Yes, it will.
So then why are we
have a single criteria that
Yeah. But it is false, right? You agree? Fermi liquid theory is false. So now... No. Fermi liquid theory has been around for more than half a century, so it's too late to say it has a criterion. Either it is true or it's false.
I don't think you can say the Fermi liquid theory is wrong.
Good.
See, you must understand
That's my
where
point.
the Fermi liquid theory is applied.
Very
for.
good.
See,
Excellent.
This is the fundamental mistake people make. The BCS theory, if you read it, it is poetry. Okay? It's fantastic. It has predicted everything. But they made a small thing on TC. People are holding on this TC for far too long. It is used and abused. So you can't say that the theory is wrong because it didn't say the TC. Because you must understand how the TC has come about, what are the parameters which go into
Ramki, I 100% agree with you, and this is a point, actually I have a published paper on this in Current Science. My entire point is that when a theory doesn't agree with experiment, it doesn't get falsified, and you just have given the reason. So therefore, we keep saying falsifiability, but it means nothing.
Yeah, a couple of comments and a question. The comment was the particular thing that Sunil mentioned there. It comes with a caveat. Yeah, there are caveats to.
Mike, please, I can't hear you well. No, just hold it closer.
Okay. So the applicability of Fermi liquids comes with some caveats if you take it outside. So, yeah. Okay, so that's one thing. Second thing I wanted to mention was one of my earlier comment probably got interpreted as saying that I don't like applying QFT to condensed matter system. Please don't think that, CFT and Chern-Simons theory are basic ideas from where quantum Hall effect, which I mainly work on, gets explained. So that's my question. Critical for, to Sachin. So you mentioned momentum space CFT calculations. Is it just another way of calculating, or do those models apply to some critical phenomena system?
So it's not a model. It's just a full conformal field theory in new formalism. So it would then be applicable to whatever physics that you have studied in Poisson space, whatever. It's applicable to everything. It's just rewriting the same thing in a different language. But the important thing over here is that the rules like OPE, etc., has to be completely rethought through. There is nothing called OPE in the momentum space. So one important aspect of CFT, which is OPE, one has to reinterpret. In my belief, this geometrical picture that I was talking about will be of fundamental importance to understand those.
Yeah, so I had a question for Sunita and maybe also generally. So you mentioned black hole mimickers. I was just curious to know what are the predictions and what is it that people are arguing? And the other thing is, do you hope to learn, for example, like the graviton mass was constrained or the speed of the graviton was constrained with these gravitational wave observations? Are there other parameter spaces which you hope to learn from these gravitational wave observations, or do you just need the black holes to be too low mass and currently we can't see them?
So actually, I'm not an expert on gravitational waves. I don't work in that. Black hole mimickers are anything which you can think of as some stars, for example, okay, or fuzzballs. These are some of the black hole mimickers. So why I said I think there's an incontrovertible evidence for black holes is because of the quasi-normal modes. So what you have to do is you have to come up with some clever mimickers which have the same kind of quasi-normal mode structure in the gravitational wave signal as you get from a black hole. They are actually very strong signatures of black holes. Yeah, we have seen the quasi-normal modes of a Kerr black hole.
Okay.
We have observed that, but there are always things you can come up with which are very similar, which have very similar signals. But I think that this Kerr quasi-normal mode is a very strong evidence for a black hole.
Okay, in the interest of time, and also since Karl Popper actually was mentioned, the context in which Karl Popper actually brought up this discussion was the demarcation problem, where essentially the demarcation was between the science and the pseudoscience. Okay, because I think Karl Popper the theories were cute in the sense it is important to actually demarcate, but there is also subsequent revisions of that particular theory. Thomas Kuhn's paradigm shift is probably more consistent with all the things what we are now trying to discuss. That issue actually of the discrimination or demarcation problem is important between the demarcation between science and pseudoscience. But here I think the arguments are actually much more nuanced, and one should actually be a little bit more paying attention to what specific theories and experimental kind of exchanges are happening. So therefore I would always emphasize it's great that we brought Karl Popper into discussion, because philosophy of science is equally important for us to take into. There's one.
Just to comment on what Sunil said, I also don't think Fermi liquid or any other theory will have will applicability everywhere. So every theory comes with a certain domain of applicability. But having said that, I think I also agree what Shiva wanted to point out. I think it was a loose comment on I think Deeptimai's joke, that every theory at least should be, if not falsifiability or testifiability, should be there. So, I mean, that's what I think Feynman said, that however beautiful a theory is, there should be some testifiability. So, I think that's what Shiva meant to say.
See, I agree with Popper that demarcation between science and pseudoscience is very crucial. In fact, one of the pseudosciences I think he was discussing was Marxism of all things.
In fact,
anyway,
he actually, you're right. In fact, he became, by the way, if somebody really reads his history, that's precisely the right issue. Yeah.
Anyway, however, my view is that in science, we actually, in practice, we may talk falsifiability, we never use that criterion. Nobody has ever used that criterion. The correct criterion to use is utility. Does a theoretical formulation teach us something that we are happy to know, that is interesting, that teaches us about some system? If it teaches us about a system, if it's useful in learning a system, we keep using it till a better formulation comes along. That is the historical
Okay,
fact.
in the interest of time, in
We have time. We have time. Okay, so 1 minute. So I think I think I think we were probably talking about two different things, and I agree with both Sunil and also Siva. So you see, when we say that a theory is consistent, we usually say that it's consistent with all the basic rules of physics. Now, many such theories can be consistent, but they will all not be realized in nature. Nature will choose one of them. And that's where experimental falsifiability is important. And that's what I meant, that from theoretically, we'll get 50 different theories which are all theoretically consistent. I repeat that, which are consistent with the fundamental laws of, say, special relativity, quantum mechanics, unitarity, and so on. But nature will choose one of them. So the rest 14, you may say they are false. I will not say that they are false. They are consistent theories, but they are just not realized in nature.
So let us thank all the panel members for a fantastic discussion. Very, very engaging.